So, imagine you are just standing in the ocean on a totally calm day,
Sounds nice.
right? And a 1 foot wave rolls in and just sort of washes against your knees.
Just a tiny bump.
Exactly, just a tiny bump, nothing to worry about at all. And naturally, your brain assumes that, like, if a wave comes along that is twice as tall, so a 2 foot wave is just going to hit you twice as hard.
Which makes logical sense, but it is completely wrong.
Yeah, it doesn't do that at all. Because of this hidden mathematical rule that's basically baked into the very fabric of our reality, that 2 foot wave actually hits you 4 times as hard.
It is a pretty brutal reality of physics, honestly.
Mm,
Small changes in the physical world, they frequently result in massive, like exponential consequences.
right.
And it is a perfect example of why the mechanics of energy are just so incredibly important to understand. And not just for physicists, but for anyone who interacts with the physical world,
Mhm.
which is, all of us.
All of us, exactly. So today we are taking a deep dive into the hidden rules that govern all of that movement. We have this really fascinating presentation deck in front of us.
Yeah, it's called mechanical waves, the architecture of energy in motion.
Right. And our mission for you today is to decode this architecture. We are going to completely bypass all the intimidating jargon, the blackboard equations, and just show you that you do not need a PhD to understand the fundamental rules of reality.
You really don't.
We're going to unpack how a vibrating guitar string, a medical ultrasound, and the destructive power of a tsunami are all playing by the exact same set of rules.
Because the physical world we navigate every single day is governed by a very elegant, highly predictable system. When you actually understand the basic mechanics, well, the things you hear, the way the ground vibrates, the way energy moves, it all suddenly makes sense as a single unified process,
Totally. So let's start right at the beginning. If you look at slide 1 here, we have the most basic concept of all, which is the transition from absolute stillness to motion.
right? The slide shows this visually as a completely flat horizontal line.
Yeah, absolute zero activity. But then a disturbance happens. That flat line begins to curve, it rises and falls, and it transforms into this flowing wave.
It's basically the visual birth of energy in motion.
Exactly. But to really understand this, we need to move to slide 2 and define what we are actually looking at. The core definition they give us here is that a mechanical wave is a disturbance traveling through a material. And that material is called a medium.
Right. The medium is just the physical substance. So it could be water in the ocean, it could be the steel of a bridge, or it could just be the air we are breathing right now.
Okay.
But the crucial distinction to grasp early on and why the medium is so important is that mechanical waves absolutely require this physical material.
No material, no way.
Exactly. If you remove the medium, the energy has nowhere to go. It has no way to travel.
I was trying to find a good mental image for this for an absolute beginner, and I kept coming back to a crowded sports stadium.
Oh, that's a good one.
Right. You have 80,000 people sitting in their seats. And suddenly one section decides to, do the wave.
Right.
People throw their arms up, they stand, and they sit back down. Now, the people in those seats, they are the medium. The individuals themselves do not run around the stadium.
No, that would be chaos.
Yeah, the guy in section 104 doesn't magically sprint over to section 204. He just stands up, maybe spills a little bit of his drink, and sits right back down in his exact spot. But the pattern, the actual disturbance itself, travels all the way around the arena.
The stadium analogy is honestly incredibly accurate because it perfectly illustrates the central law of wave mechanics, which is that waves transport energy, not particles.
Not particles, right?
The people in the stadium have a net displacement of zero. The energy of the crowd's excitement is what commutes around the building, while the particles, the people, effectively just work from home.
Work from home. I love that.
They move, they transfer the energy to their neighbor, and then they return to their resting state.
Okay, so knowing that the energy commutes while the particles just stay put, that gives us a great foundation for slide 3. This one breaks down the anatomy of a wave into basically 3 vital signs.
Right, the basic anatomy.
First, we have amplitude, which is the maximum height of the wave from that flat center line. Then we have wavelength, which is literally the physical distance between 2 consecutive peaks.
Like measuring from the crest of one ocean wave to the crest of the next one.
Exactly. And finally, period, which is just the time it takes for one complete cycle to finish. But, if the energy is always moving and the particles are just bouncing around, the next logical question is, do all waves move in the same way?
They definitely do not. How the energy moves through the medium depends entirely on the shape or the morphology of the wave. And
Mhm.
slide 4 introduces the two main morphologies that govern, well, almost everything we experience.
Okay, and the first one is called a transverse wave. This one feels super intuitive to me. It features perpendicular motion.
Yeah.
So, like, if you and a friend are holding the ends of a jump rope and you whip your hand straight up and down, what happens?
You get a wave.
Yeah, you are creating a vertical motion, but the wave itself races horizontally toward your friend. Your hand goes up and down, but the energy travels forward, perpendicular.
Plucking a guitar string operates on the exact same principle. The string vibrates vertically, but the sonic energy is carried outward. That up and down motion driving forward progress, that is the absolute hallmark of a transverse wave.
Well, okay.
But the second type, the longitudinal wave, operates very differently.
Right, longitudinal waves feature parallel motion. So instead of a jump rope, imagine a classic slinky toy stretched out flat on a table.
Yeah.
If you grab one end and shove it straight forward and then pull it straight back, you aren't creating an up and down shape at all. You create these dense, bunched up sections of coils that travel horizontally down the length of the toy.
Right, they kind of pulse forward.
Exactly. The motion of your hand is parallel to the direction the wave is traveling.
And that parallel push and pull is the exact mechanism of sound. When you speak, your vocal cords aren't sending a physical, wavy string of air up and down through the room.
Right.
They're acting like your hand on that slinky. Your vocal cords push and pull against the air molecules in your throat, creating this microscopic bunching effect.
Wow.
Those molecules bump into the next molecules, transferring the energy, and that microscopic slinky effect travels across the room until those bunched up molecules physically shove against the eardrum of the person you are talking to.
Which is just a wild way to think about a conversation. Like when I am talking to you right now, I am literally playing the air in this room like a slinky compressing oxygen molecules to physically touch you.
It is wild, but it's exactly what's happening.
But beyond just understanding how my voice reaches your ear, moving to slide 5, the research outlines some incredible real world applications for these parallel and perpendicular motions. Because why does this matter outside of a physics classroom, right?
We actually rely on these mechanical principles to effectively see the unseen.
See the unseen. Okay.
Because we know how these waves behave, and we know they require a medium to travel, we can use them for complex spatial navigation and medical diagnostics. Think about sonar,
Oh, sure.
bats hunting at night, dolphins navigating murky waters, and submarines deep in the ocean. They all utilize longitudinal sound waves to see. They emit a pulse of energy into their medium air or water, and then they just wait.
Because the energy has to hit something to bounce back. It's kind of like standing in a pitch black room and throwing a tennis ball at the wall. You cannot see the wall, but when the ball bounces off and hits you in the chest, you know exactly how far away the wall is, based entirely on how long it took the ball to return.
Exactly. And we have adapted that natural mechanism for medical technology, like ultrasonic scanners.
Right, for pregnancies and stuff.
Yeah, when an expectant mother gets an ultrasound to check on a baby, the machine is sending high-frequency mechanical waves into the body. Those waves hit different tissues, muscle, bone, fluid, and they bounce back at slightly different times because of the different densities of those mediums.
Oh, wow.
The computer calculates the minute time delays of those millions of bouncing waves and translates them into a real-time visual map.
Yeah.
It is quite literally using sound to construct sight.
That is essentially a superpower harnessed through basic mechanics. I love that. But to harness it, we have to understand the math. And this brings us to slide 6, a section titled The Mathematical Pulse.
Here we go.
Now, I am going to push back here on behalf of you, the listener, because looking at the equation provided to map these waves, it is incredibly intimidating.
It does look like a lot.
It reads y of x and t equals a times the sine of omega t minus kx. I mean, it looks like someone dropped a bowl of alphabet soup. How do we translate this into something an absolute beginner can actually visualize?
It does look like a dense wall of calculus, I'll give you that. But it is actually just a very precise sentence describing a moving picture. The equation is designed to track a wave as it moves through both physical space, which is represented by the x,
Okay, x is space.
right, and time, which is the t. The sine part just means it has that smooth, rolling, repeating shape.
Okay, so we are tracking space and time, the x and the t, but what are the other dials in this alphabet soup doing? Like, what is omega and k?
The a at the front is just your amplitude, how tall the wave is.
Right.
Inside the parentheses, you have two specific tuning dials. The first is omega, which represents the angular frequency. You can think of omega as a clock. It tracks how fast the wave is oscillating in time.
Okay, omega is the clock.
The second dial is K, the wave number. This tracks the physical stretch. It tells you how compressed or elongated the wave is in physical space. So when you strip away the Greek letters, the equation is just asking three simple questions. How tall is the wave? How fast is it ticking? And how physically stretched out is it?
Okay, that feels much more manageable. Just tracking height, timing, and stretch. But logistically, moving to slide 7, this seems like a nightmare to actually measure.
How so?
Well, how do you measure something that is constantly changing its shape in physical space while also constantly moving forward through time? If I try to measure a moving car while I'm also running alongside it, my measurements are going to be a mess.
That is the core dilemma of wave mechanics. And the solution involves one of the most elegant tricks in calculus, which is using spatial and temporal derivatives.
Okay, big words. Break that down.
Because tracking both space and time simultaneously is too chaotic, you have to isolate one variable by basically freezing the other.
Freezing reality.
Exactly.
Yeah.
Let's say you want to understand the physical shape of an ocean wave. You freeze time, you take a high-speed photograph, time is stopped, and now you can take a tape measure and easily track how the amplitude changes across physical space. That is your spatial derivative.
Okay, so I pause the universe, walk right up to the frozen water, and measure it. Makes perfect sense.
Conversely, if you want to understand how the wave behaves over time, you have to freeze space. You pick one single fixed location.
Like staring at one spot.
Right. Imagine standing on a pier, looking straight down at one specific molecule of water. You ignore the rest of the ocean. You just watch that one molecule bob up and down as the clock ticks. You are measuring how the wave changes over time at a fixed position in space. That is the temporal derivative.
So you either freeze time to measure space, or you freeze space to measure time. By isolating them, you can map the whole system.
Exactly.
And that concept leads directly into slide 8, what the source material calls the universal wave equation. It takes the spatial math, it takes the temporal math, and it drops them into one master formula. So, what is the grand takeaway from locking these two measurements together?
The profound realization of the universal wave equation is that space and time are not acting independently. The spatial derivative and the temporal derivative are permanently bound together by one single variable, the speed of the wave.
Wait, really? So, speed is the glue. If I know how the wave wiggles through time and I know its speed, does that mean I automatically know its physical shape in space?
That is the exact mathematical consequence. Because the speed dictates the relationship, any change in the wave's shape over time is directly, inextricably tied to how it stretches through physical space.
Wow.
The universe enforces a strict, unbending ratio between space and time, and that ratio is governed entirely by the speed of propagation.
So, space and time are basically sitting on a seesaw, and speed is the fulcrum balancing them.
That's a great way to look at it.
That is brilliant. Which brings us to the next massive question on slide 9. What actually determines that speed? If speed is the master controller of space and time, who is controlling the speed?
Well, it depends entirely on the medium. If we go back to our transverse waves, the jump rope or the guitar string, the speed of the energy traveling down that string is not random. It is dictated by the physical properties of the string itself and what the research describes as a physical tug of war.
A tug of war between what?
Between tension and mass. Tension is the restoring force. It is the tightness of the string fighting to snap back to that flat, still horizontal line.
Right.
Mass is the inertial resistance. It is how heavy and sluggish the physical material is, fighting against being moved in the first place.
Okay, so imagine holding a thick, incredibly heavy soaking wet rope versus holding a thin, lightweight, tightly wound guitar string.
Right.
If I snap the wet rope, the wave moves really slowly because the mass is huge and sluggish. But if I pluck the tight guitar string, the tension is massive and the mass is tiny, so the wave moves incredibly fast. The speed of the wave is just the final score of the battle between tightness and heaviness.
The math confirms your intuition perfectly. The equation provided for transverse speed is the square root of tension divided by mass. Higher tension equals more speed. Heavier mass equals less speed.
Makes sense.
But that is just for solid strings. When we transition into slide 10, we're looking at fluids and ideal gases, like the air transmitting our voices. The rules of the tug of war change.
Right, because I can't tighten the air in this room like a guitar string. And looking at slide 10, the notes outline the speed of sound through gases, and they list some really heavy variables here. bulk modulus, fluid density, molar heat capacities.
It looks intense.
Yeah, but nestled inside all of that complexity is one dominant, highly intuitive factor for the speed of sound in the air, and that is temperature.
Temperature is the ultimate governor of sound speed in an ideal gas. And slide 11 provides a very clear, concrete calculation to prove this.
Okay, let's hear it.
At 0 degrees Celsius, which is freezing, or 273 Kelvin, a sound wave travels through the air at roughly 10.5 zeros per second. But on a warm day at 27 degrees Celsius, the speed of that exact same wave jumps up to 11.01 meters per second.
So sound travels faster when the air is hot. If heat is just thermal energy, does that mean a hot room is literally primed to pass the sound along because the molecules are already jittery?
You've hit the nail on the head. On a microscopic level, heat is simply kinetic energy. In warmer air, the molecules are already vibrating, moving, and bouncing around very rapidly. Because they are highly energetic and agitated, when a sound wave impacts them, they pass that mechanical push to their neighbor much faster.
It makes me think of a relay race. Like if you are trying to hand a baton to the next runner, and that runner is already jogging in place, warmed up, and bouncing on their toes, which is our hot air, the handoff is going to be incredibly fast.
Oh, exactly.
But if the next runner is freezing cold, stiff, and standing completely still, it takes significantly more time to get them moving and pass the baton. Cold air is sluggish, so the sound wave just kind of plows through it more slowly.
And that sluggishness affects everything from acoustic engineering in concert halls to how animals communicate in different climates, which perfectly sets up the final pillar of our deep dives today, the actual architecture of sound and power.
Right.
We established that sound is a longitudinal wave playing the air like a slinky. Slide 12 visualizes this architecture as zones of compression and rarefaction.
When I look at the diagrams of compression and rarefaction on slide 12, it really brings the physics into the physical body. Like compression is where the air molecules are shoved densely together, creating high pressure.
Right.
Rarefaction trailing right behind it is where they are spread far apart, creating low pressure. So when I am at a concert and a massive bass drop happens, I am not just hearing it, I am feeling a high pressure wall of compressed oxygen physically slamming into my chest and my eardrums.
You are experiencing the direct transfer of mechanical power. And that transfer brings up the ultimate question of wave mechanics, which slide 13 covers. Where does the energy actually live while it is traveling?
Yeah, where is it hiding?
The research reveals that the energy inside a mechanical wave is split into a perfect 50-50 partnership
A partnership between what?
between potential energy and kinetic energy. Half of the wave's total energy is potential, which comes from the elastic stretch of the medium.
Okay, the stretch.
Right. Think of the physical effort it takes to stretch a thick rubber band that stored elastic tension is holding half the energy. The other half is kinetic energy, which comes directly from the actual velocity of the medium moving up and down. The stretch and the speed share the energy burden equally at all times.
So the elastic stretch and the actual motion are splitting the bill 50-50. But how big is the bill? Like, how much power are we actually talking about?
This brings us back to that terrifying mathematical rule we opened the show with.
Slide 14. Looking at the total energy and power output formulas, there is a massive detail highlighted at the bottom here. Energy and power do not scale linearly. They scale with the square of the amplitude and the frequency.
This is arguably the most consequential physical rule for engineers, architects, and really anyone living on planet Earth to understand. The square law is ruthless.
Let's apply the square law to that ocean wave we talked about in the intro. Amplitude is the height of the wave. If a 1-foot wave hits you, it has a certain amount of energy. If you double the height to a 2-foot wave, you aren't doubling the power. Because the math dictates that the power is squared, 2 squared becomes 4. It packs 4 times the destructive power.
It escalates so quickly.
If a massive tsunami goes from a 10-foot crest to a 20-foot crest, it doesn't just hit the coastline twice as hard. The energy output is quadrupled. Tiny incremental changes in the height of a wave create massive exponential explosions in power.
It is exactly the reason why a minor uptick on the Richter scale during an earthquake doesn't just rattle some extra windows, it exponentially increases the structural damage to a city's foundation.
Ow!
It is why loud noises scale so quickly into permanent deafness. The universe does not deal in simple addition when it comes to wave power. It deals in violent multiplication.
Which really ties this entire deep dive together as we look at the master blueprint on slide 15. We started with a flat, still line and we watched it curve into energy. We figured out that this energy uses materials like air and water to commute, while the particles just bounce in
Right, the
place.
core principle.
We looked at the two morphologies, transverse jump ropes and longitudinal slinkies. We realized that speed is the master glue holding the wave equation together. And finally, we saw how that energy can square itself into just exponential power.
We've basically covered the complete architecture. It shows how an elegant, foundational set of physical laws dictates a massive portion of the reality we interact with daily.
It is incredible how accessible it actually is once you look past all those Greek letters and just observe how the world physically pushes and pulls.
It really is. But there's one final implication of this architecture that I think is worth pondering before we finish.
No, lay it on me.
We established very early on that mechanical waves only transport energy, not matter. The particles simply wiggle in place and return to zero.
Right.
Now, think about the human experience.
Hmm.
Our entire perception of the physical world relies almost exclusively on these transferring pulses. The voices of your friends are just pressure waves vibrating your eardrums. The warmth of the sun is wave energy.
Even touch, right?
Exactly. Even the texture of the chair you are sitting in is interpreted by resistance and pressure waves traveling up your nervous system.
So, wait, if our brains are just interpreting energy bouncing through mediums,
Exactly. If
it
everything we see, hear, and feel is just the result of energy passing through materials that are otherwise just sitting perfectly still, is our sense of a hard, solid, permanent physical reality just a beautifully constructed illusion?
oh, wow.
An illusion built entirely by the architecture of intersecting vibrating energy.
Now that is a deep dive. Catch you next time.